required to maintain logic consistency 5 to 10 at the bottom here, 5 to 10 kT over Q. Okay, we went over this chart, which shows that for digital binary circuits, we have so-called logic compression. In other words, for example, this two-way NAND, there are two inputs, so altogether there are four possibilities. Okay, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. Four different combinations, but output is only two, 0 or 1. Okay, so for this to be accomplished, we need the transistor has to be nonlinear. Okay, nonlinearity is required for digital logic circuits. And so if we look at the semiconductor transistors, for example, for diode, diode current is exponential QE over KT minus 1. This is nonlinear only if V is much larger than KT over Q. Because if QV over KT is much less than 1, then the current is simply proportional to QV over KT, and that's a linear behavior. So for nonlinearity, for semiconductor device to be nonlinear, the QV over KT must be much larger than 1, which means that V is several KT over Q. Okay? And furthermore, I showed that the simulation study, the model, go through the circuit model, you can show that when there are different combination scenarios, you can have zero or no noise margin once VDD is too low, okay, below something like 3 kT over Q. And also there's a table here. Yeah. So that's the basis of, I said earlier, on the order of 5 to 10 kT over Q, in order to have enough nonlinearity to carry out the logic circuit function for digital circuits. Okay. Next question. Refer to this chart, the bottom line comment here. When limited by lateral fields, IK does not help. Okay. But first of all, what is lateral field? Lateral field refers to, in this case, we consider this interface, dielectric boundary, AF. Vertical field means perpendicular to the interface. So that's in the X direction. Lateral field is in the Y direction. Okay, so you can see that that's the vertical direction. Okay, vertical field or normal field, perpendicular field, and the lateral field is in parallel to the interface. Okay, so only the vertical field is multiplied by the permittivity. In other words, this is displacement, vertical displacement continuous. In the lateral case, either field or potential is continuous, and there's no permittivity, no dielectric constant here. And so we go back to this picture. So this shows the lambda solution for different thickness and different dielectric constant. And in this lower right corner, okay, the lambda is approximately given by, well, first of all, let's explain the simple case, the one case. One case means that epsilon silicon and epsilon oxide are the same. in that case, okay, if they have the same, then it's essentially one region. If it's one region, then lambda is given by the height of this rectangle, basically WD plus Tx. But if dielectric constants are different, like SiO2, then we are talking about if this is factor of 3, for example, for SiO2, this is WDM plus 3Tx, which makes the scale length larger than the physical dimension because of the permittivity of oxide is smaller. Let's follow this curve here. But this approximation indicated by the dotted line doesn't represent the curve. Once the once oxide is thick, because this corner is when oxide is very thin. But when oxide is thick, then all 4 different curves merge together. And so in that case, the lambda is independent of the dielectric constant. So that's why the comment, see. Okay. So if it's independent of the dielectric constant, that means the lateral field, the field that's parallel to the interface when the dielectric is thick, is dominating the scale length behavior. Okay. So that's why the when oxide is thick, the lambda becomes independent of epsilon of oxide. Now, ultimately, the physical oxide has to be thin enough, okay, because the lambda is cannot be less than 2Tx, no matter what the dielectric constant is. That's this common point here. Okay. Okay. So I think that answered this question. Next question. Double gate, single gate, source drain. Well, the important thing is that the source drain needs to be self-aligned to the gate. Otherwise, the overlap capacitance, which we will cover in probably later today in chapter 8, overlap capacitance is too large. That will degrade the performance. Okay. So for single gate, self-align is straightforward. Okay, you just do the gate first and then implant through the gate with the gate in place, so that the source drain is self-aligned to the gate. But for double gate, it's more difficult to do. That's why people have to come out with FinFET kind of geometry to make both gate self-aligned, the source drain self-aligned to both gates. And the second part is for gate all around. Gate all around is like cylindrical nanowire. Okay, so that's gate all around. And there's some difference, but difference is not much. You can see from the scale length plot, for example, for nanowire or gate all around. This point here, this means Tx over lambda is less than about 0.76. In other words, lambda is larger than 1.3 Tx. Okay, so below that point. For double gate, okay, the Tx over lambda is less than half, which means lambda is larger than 2 Tx. Okay, so from this point of view, the gate all around is a little better. Okay, because for this, the lambda can go down as much as 1.3 as opposed to 2 Tx for double gate. So slightly better. Next question. Oh, So what figure determines the noise margin? Okay, I show this that basically the noise margin is given by the largest square that can be fit between a transfer curve and the counterpart complementary transfer curve in red. So in other words, the more skewed transfer curve is, the better. And transfer curve, of course, is the output versus the input. That's generated from, in this case, it's NMOS and PMOS. Right? We generated A, C, E, D, B. Okay? And so we want a sharp slope, which means that we need a saturation. So this is very sharp because E is in saturation. Both NFET and PFET are in saturation. So saturation is very important for noise margin. If the current is a straight line with no saturation, then the transfer curve is straight. There's no steep part. Then the noise margin is poor because then the square that can fit here will be small if the curve doesn't have a sharp transition. Okay, so the key is to have a sharp transition in the transfer curve, which is achieved by having a good saturation region in IV, both N and PFET IV characteristics. Okay, last question.
Yeah.
Sun Yan here. Okay, go ahead, please, Jack.
Okay. Last question is what roles does the use of high K dielectric hafnium oxide play in sensing performance? These devices and then what challenges drive in terms of mobility? Okay. I think like Hao Lao Shi, introduced scaling the high K all the concept. Actually, independent of the channel material, we try to scale in the traditional sense, the geometry or the gate length. We need to be able to thin down the oxide thickness from a gate control standpoint, but there's a direct tunneling limit. So once you get to very thin oxide, there will be direct tunneling gate leakage, which we don't want. So that's why we use high K, making the physical thickness 就是它实际的那个物理的厚度是比较大，但是它电性上是比较薄的，可以 control。那这个是无关于那个 independent of the material， 但是呢 ，IK material even just in the silicon channel, there's always some intermediate like IL, what we call the SiO2 or SiOX, very thin layer. So that interface, actually after many decades, after many years, what we know the best so far still silicon dioxide and silicon interface. Okay. So and also IK because of like hafnium oxide, you have metal, and once you get in contact with semiconductor, you may have gap states, the Schottky barrier issues. So basically, we need some interlayer also. Okay, and in terms of the germanium or 3-5 channel, they have different considerations too. So whether you have a native oxide or you need to, again, to be able to have a good interface that doesn't degrade the work function or the mobility. Okay. Okay. So now the second half of the question, I'm not sure exactly what the question is about, but I can try to, expand a little bit。那个 High K 的这个材料，它本身是极化的，有一些像铁电啊这种啊，有 polarize，OK，那个呢，它就会造成一些就是说叫做 soft optical phonons 啊，很高频的那些那这些也会影响那个 mobility，所以 High K doesn't come for free。但是因为 High K 不能用 polysilicon gate 了，必须要用 metal gate。那现在用的这个 metal gate 其实对这部分的 mobility 的那个影响呢，反而有帮助啊。它事实上是 metal gate 呢，如果说有比较高的 electron concentration 然后还有这个叫 d effective mass 跟那个 permittivity 的话在 gate electrode 这一端，它是可以第一方面降低 Coulomb scale 的，第二个呢，它也会减少这种 optical phonon 它的 coupling 跟那个 inversion diagram， 所以基本上目前的这个 combination 就是说 High K metal gate 在整个这几个很多个 effect 综合起来的时候就说我们没有 High K 就不用再 scale 这个 gate length。那有了 metal gate 有其他的这个好处所以补回来。另外那个有些 High K film 事实上呢也可以像 germanium channel 或者是 silicon germanium channel， 你可能你需要一个 silicon 上面的一个 cladding， 或者是我们在germanium 上面可以直接摆一些 aluminum oxide 或什么那些，因为 germanium 本身有一个很讨厌的东西，那个oxygen 会造成 germanium oxide 是一个 volatile， 是不稳定的一个东西，会造成那部分的那个缺陷所以我想大致就是 qualitatively 就是会有这些好处坏处一些 trade off， 但最后呢，我们的确是不能没有 High K。然后有了 High K metal gate， 刚刚陶老师讲的一些有关那个 gate all around， 还有这个要 self-aligned 的 gate all around structure。因为要做 High K metal gate， 其实都是 replacement gate 的嘛那也很自然的从 FinFET 做到我们叫做奈米片事实上是可以用这个那个polysilicon 这一类的然后就一路吃下来，最后把那个 nano 系或者是 FinFET 那个比例出来nano 系那再包回去的时候可以做 wall function tuning， 然后也可以整个把 metal gate 做包起来，就变成利用这个结构跟制程上的办法，让它可以做self-aligned 这种multi gate 或者是 gate all around 的 construction 我想有些跟 mobility 相关，跟那个这些呢，参考一些这个 reference 那这个要谈起来是可以谈几个钟头，所以给大家一个参考接下去如果有空大家要探讨的话，可以再另外讨论谢谢。那个陈老师讲。
So we go back to where we left off in chapter 8 last Monday.
Yeah, we are already here. You were sharing, but then you stopped sharing.
Yeah, that's but I cannot see it somehow. Let me see.
Okay.
Don't know what's going on here. Oh,哎，现在可以了吗？Source drain
有
series resistance.
Yeah, yeah.
Okay.
有 Okay.
All right. So next part, parasitic resistance and capacitance. Okay. In chapter 5, 6, 7, we talk about the intrinsic MOSFET that does not include any parasitic resistance or capacitance. Okay. So this section covers the extrinsic or parasitic resistance between the intrinsic MOSFET and the contact. Okay. So first, the source drain series resistance is shown here. Basically, from the the source, the MOSFET source to metal contact, there's a resistance called RS, and on the drain side is RD. So that has an effect. The prime the number of the intrinsic voltage. Okay, without prime, those are applied. So applied BGS, VDS, but the intrinsic is less than that because of the resistance. Okay? And so as you can see here that the intrinsic gate resistance is reduced by the voltage drop across the source RS. Okay? And for the drain resistance, it enters in the VDS, VDS prime part. So the source resistance actually is worse because it degrades both the gate to source voltage and also degrade the drain to source. The intrinsic resistance, okay, we covered in chapter 5, is looks like this, which goes down as the channel length. But the series resistance, which is also proportional to 1 over W or the device width, but there's no length dependence. So when the device becomes shorter and shorter, eventually the parasitic resistance becomes more and more important. The typical number that the technology has achieved is in this ballpark. It's about 100, 200 ohm micron. This is ohm micron because the resistance is per width. So this resistance times width is constant. So if width is doubled, then the resistance will be reduced correspondingly. And by the way, the intrinsic channel resistance has the same width dependence. Now, if you look at where the origin of the series resistance, in this model, it divides into 4 components. The first component is under the gate for the accumulation. Because of gate voltage, even though this is N+, but it's the gate voltage makes it even higher electron density. So that's this part. And then the current will flow from the inversion channel, which is very, very thin, to the more or less uniform over the junction depth. And so it flows over, and this is IR, there's a resistance drop depending on the length of the source drain. And then the last component is the contact resistance, flowing from the source drain into the metal contact here. Okay. And now, so this is for a standard MOSFET, but nowadays we have a so-called self-aligned silicide. Okay? Self-aligned silicide that will greatly reduce the series resistance. Okay, and let me just show how. Okay, just schematically how this is done. Is this is introduced below something like half micron CMOS technology generation. So, so after we pattern the gate and then implant the source and drain, we put on a either oxide or nitride, and then we directional etch out the film on top of the gate and the source drain, but left spacers, okay, between the gate and source drain. And then we put on a metal. Initially it was titanium, later on cobalt and then nickel, and then we heat it up to form silicide. Okay, titanium silicide, cobalt silicide, or nickel silicide. And then after that we etch off the unreacted metal over the spacer so that it's not shorted. And then so it looks like that. So we have a silicide only on gate and source and drain, and it's self-aligned because the metal on the spacers are removed with a selective etch. So this greatly reduce the series resistance, because now the distance between the so this is silicide. First of all, just give you some ballpark figure. The metal, of course, is like aluminum or copper. It's very conductive. 0.05 ohm per square for some 1 micron thickness. And for the source and drain region, N plus P plus diffusion, let's say it's 0.1 micron deep. This is many orders of magnitude higher, 50 to 500. Silicide is in between. You can see the silicide is a factor of 10 or more better than source and drain, or N plus P plus diffusion, but still more resistive than the metal. Okay? But it helps. So once you have a self-aligned silicide shown here, so that's the titanium silicide, let's say. So all the silicon region between the gate spacer and the thick oxide isolation is form silicide. And so now that reduces the resistance of the source and drain. Also, the current will flow right through, right over to the silicide because it is much more conductive than source and drain. So that reduces the contact resistance, okay, and they make a long contact case. But nevertheless, when the gate is shrunk, I have one case to show you. In this case, this actually is the experimental data of a 20 nanometer bulk MOSFET. That's probably the shortest that can be made. And those are the black curves. Now, if I model this with no resistance, you can see that those are the colored dots. That's the model. The blacks are published data. And so we can see that RST has reduced, let's say, the current in the saturation region by about 30% or so. And so that's pretty much the shown here. Okay, that's this 100 to 100 ohm micron. That's the best we can do because because the source drain doping limit is about 10 or 20, and it cannot be much higher than that. That's the solubility limit. Okay, so even with psilocybin, without psilocybin, it's much worse than the number I just used. So this is all with self-aligned psilocybin. Okay, next is capacitance. There are many capacitance components. Some we call it intrinsic, and intrinsic is the gate capacitance, of course. That's due to the inversion charge. To turn the MOSFET on and off, you have to induce inversion charge, mobile charge. You turn it off, you take the charge out. So that charge and discharge of the gate capacitance. So that's intrinsic. That we discussed at the end of chapter 5, I think. Okay. But the parasitic components we have is shown here. The mainly junction capacitance and overlap capacitance. Overlap capacitance is between the gate and source or gate and drain, and those course you cannot avoid that. Drain junction is important because of the you have to switch the drain on off. For example, if you look at let's say the original CMOS. So the drain, when you switch the input, the output goes from 0 to VDD. So that means the drain has to go up to 0 and VDD. So that's the capacitance that will slow down the switching speed. Okay, and then C overlap is even worse. We'll discuss this effect in the next few charts. But here are some standard formula for the depletion capacitance under the channel and also the junction capacitance of source and drain. And okay, so this chart is focused on overlap capacitance. Overlap capacitance itself has different components, 3 components. First one is direct overlap. It's direct under the gate. And this we minimize with the self-aligned gate process. That's why the self-aligned gate is so important, because otherwise, to make sure that you have no underlap, at some part of the wafer you can have too much overlap, and that will increase the direct overlap capacitance. But even with self-aligned gate process, you still have some direct overlap with a minimum overlap length. In addition to that, you also have fringe capacitance. Fringe capacitance, inner fringe, and they have expressions given by this. This was you can read the reference from the book. This was the derived by conformal mapping of this structure. Okay. So in any case, for a typical value of gate thickness, the and overlap length about 2 to 3 times T-ox. Okay, the overlap capacitance per width. Of course, if you multiply the width in the perpendicular direction, the capacitance goes up. It's about 0.3 femtofarad per micron. Okay? And that's independent of technology generation. It's possible to do much worse than that if you don't if you have too much overlap, direct overlap. but it's hard to get much smaller than this figure, 0.3 femtofarad per micron per edge on each edge. Yeah. The next one is the gate resistance. Gate resistance happens when this is the device width direction. Okay, so let's say the gate contact is on the left. So when you change the voltage from the gate contact on the left, that voltage has to go through all this resistance to get to the other side, which is no contact, let's say. And so this is like a distributed RC. R is due to the gate resistance. As simple as rho G is the gate resistivity. Okay, let's go back to the self-aligned. So with self-aligned silicide, you form silicide over the gate, and that helps the gate resistance a lot, because otherwise you have a polysilicon, and that's even worse than source and drain resistance. Okay, so with silicide, but still it can be a problem if the width is too long. Yeah. So this can be modeled by a distributed RC, like transmission line kind of thing, and that's given by this propagation, okay, the wave propagation equation, and the RC delay is estimated to be equal to this. And so rho G is the resistivity of the gate, and Cox is the capacitance. But the important thing is that proportional W square. Yeah, of course, the wider the gate, it doubles the resistance. If you double the width, it double resistance, and also double the capacitance. So this also goes to W square. So the width is very important that we have to minimize. Give you some numerical example. For the gate resistance 10 ohm per square, 50 angstrom oxide, of course, nowadays much thinner than that. So and the delay due to the gate resistance, assuming a 7.6 micron gate width, is about 1 picosecond. Okay. So but we can. So that means that if you want more current, you don't want to just increase the device width. Rather, you use the multiple finger layout. Okay, as shown on the next chart. So instead of a very wide MOSFET, you make a so-called interdigitated source and drain. So you can, in this case, there are 8 gate fingers, and we have the source drain alternating. Okay, so altogether there are 8 MOSFETs. So current is multiplied by 8 without making the width any wider. And remember, if you make the width 8 times wider, then the gate resistance will go up as 8 squared or 64. So that would be too much. So the way to do that is to, instead of making the device wider and wider, we make a multi-finger layout like this. And this is standard. This is standard practice. When you have a so-called driver, that a small transistor driver, a heavy capacitive load, we need a lot of a large current from a wide device. We use this multiple source and drain in the digitated layout. Next is interconnect scaling. Interconnect scaling. So let's see, in the beginning of this chapter, chapter 8, we talk about a MOSFET scaling. But interconnect should also scale because otherwise you cannot connect all the small devices into circuits. And so this shows how you scale. You scale all the dimensions, just like MOSFET scaling. And so area goes down. This is scaling factor K larger than 1. So the area goes down by K squared, and the length goes down. Also, the insulator thickness goes down. And if you follow that, you can see that there will be a problem because the wire resistance, let's see, the wire capacitance per unit length is the same as before you scale, but wire resistance goes up, it's K squared. Okay, and so that means that now remember that the MOSFET with the resistance the MOS resistance is unchanged. So if the wire resistance becomes higher, that will be a problem. Okay? But so we discussed that here. For the interconnect RC delay, okay, given by this, and then we put in some numbers. W is the resistivity, the resistance per length. CW is the capacitance per length. Okay, so we consider in this case is metal. Metal is very conductive. Remember that I showed that metal is 0.05 ohm per square. So we put in those numbers. And also the wire capacitance, assuming there's cylindrical situation, simplified. Okay? So it's about 2 per centimeter. It doesn't change much. So you derive this number, and if it's aluminum oxide, copper is a little bit better. But if you look at the factor, material factor in front, it's a very short time, 3 times 10 to the minus 18 seconds. Multiplied by this geometrical factor is wire length squared divided by the wire cross section. W is the width, T is the thickness of the wire. And so this is dimensionless. So because the multiplier is very short, so as long as you keep this geometry factor less than something like 3 times 10 to the 5, the delay due to wire resistance is less than a picosecond, okay? Which means that it's negligible compared with the device delay. So from this numerical estimate, even though we just show that the wire resistance doesn't scale, it goes per length actually goes up, but it's not a problem because it remains small as long as the wire is not too long. But and this wire length can be short because once the MOSFET becomes smaller and smaller, the wire needed to connect them into a circuit also becomes shorter. Okay, so that's why it's called local wire. It's not a serious problem. But global wires, however, is a problem. Okay, global wires is like the length is on the order of chip size. On the order, it can be something like 1 centimeter, and so it doesn't matter how small the wire or the transistors are. The length does not scale down because chip size doesn't change much. You just put more and more circuit into the chip, and so in that case, you put this number in, you get a wire delay is 1 nanosecond. So this becomes unacceptable. Okay, and so the conclusion here is that we cannot use small wire to connect circuits far away. Okay, cannot use small wire to connect large circuits. Okay? Small wire only for local circuits. So the solution is the multiple level shown here. This shows 6 level of metal. This is the transistor and silicon chip. And then we have 6 levels in 3 pairs. We got the smallest, medium, and larger. Okay? And so by doing that, we use the large wire for long distance wire from chip to chip, one corner of a chip to the other corner. And we use this one, so that will allow the interconnect delay to be small on long wires. So for shorter wires, we use the smaller size, smaller cross section to wire the local circuits. But for global wire, with global interconnect, we use the large one until the wire delay becomes limited by the speed of EM wave. Basically, it's the speed of light. And notice that the RC delay, as we just estimated, goes as length squared. But the time of flight, or due to speed of light, is linear. Okay, so there's no, so depend on the length of the wire, there's no need to use very large wire if the wire is limited by the EM wave or speed of light. Then it becomes independent of wire size. Okay, so what's shown here is that if you use 3 different wires, 0.1 micron, 0.3 micron to 1 micron, okay, if it depends on the length. Okay, so it helps to use a larger wire, but once you hit this linear line due to EM wave, then it doesn't improve anymore. Okay, so for example, if it's the intercept is here, so for that wire, if you use even larger than 1 micron size, you still have the same delay due to the per length, due to the propagation of EM wave. Okay. And that, of course, is a universal number, 70 picosecond per centimeter. Okay. The permittivity will slow down a little bit compared with vacuum. Let's see, one more chart, and we'll take a break. Okay. Just to show you, because we obviously need multiple level of interconnects. Today's microprocessor have most likely more than 10 levels of metal. So the technology to achieve that is by planarize. Okay, but single level to make it look like this. You put in the blue is the metal, you put in contact to the gate, to the source and drain. But you build up some topography here. And so you cannot go on more than a couple of layers. If you want to go to 10 or 15 layers, you have to planarize at every level, shown here. Okay, so you have a contact, we call the contact stud, and then you planarize, you put in metal, and then you planarize again before you build the next level. Okay, so this makes it, it's possible to go many levels by using this technology. And so CMP stands for chemical mechanical partition. It polarized at every level. Okay. All right. So we take a 20-minute break before we cover the rest of chapter 8. Yeah. We'll resume at 10:10.
Okay, thank you.
And then the midterm 2 is 11 to 12 later today.
Yes, we're ready here. Thank you.
Okay. The next part is so-called, we call the propagation delay. Okay. Now, the CMOS delay, we discussed it earlier, but we assume that the rise time and the fall time is 0. Let me show you. Here, this chart. So when we say the switching for the step input, in other words, when NMOS turns on, the input goes from 0 to VDD in a step, okay? Instead of have a rise time, and same thing for the PMOS. But now we consider that the propagation delay has a finite rise time and fall time. Okay, so to model this, we can make a chain of identical inverters or NAND or NOR gates, one driving another. And at output, we just connect a capacitor in order to change the delay. If, of course, larger the capacitor, the slower the longer the delay. And all right, so this plots the V1, V2, V3, V4, which is the voltage after inverter 1. That's voltage after inverter 2. Okay, so to begin with, we have a step input to get things started. But after a few stages, the waveform become standardized. In other words, the rise time and fall time doesn't change anymore, no matter how many stages you go to. And okay, so in this case, V1 is going up, which turns on the MFET of inverter 2 that pulls down V2. Okay, and then the V2 goes down, which turns on the PFET of inverter 3. So V3 goes up and V4 goes down, and so on. Okay, after that, it just repeats after a few stages. And so with this, we can define a propagation delay. And that's equal to the pull down delay, the average of pull down delay and pull up delay. Okay, so in other words, if you measure the delay time, this case, the VDD is 1.5 volt. Right? So half VDD over 2 is 0.75, this dashed line here. And so you measure that from V1 to V2, that's the out end. It's due to the pull up, pull down MFET current. And V2 to V3 is due to pull up PFET current. And first, let's look at the switching trajectory of those devices. Okay? So for pull down transition, pull down means that you start with output of VDD, and then you turn on the MFET, and then eventually the output becomes 0. Okay? So pull down from 1.5 to 0. That's this V2 waveform, because V1 is going up. Okay? So V1 in this case is the input voltage or the gate voltage, and the output voltage is VDS. Okay? And So instead of the step input case, step input, you go from here, you jump to the highest curve, which is V equal to 1.5 volt, and then you discharge from there. So in that case, you have the saturation current, which is the highest. But for propagation delay, you go through different input voltage. Okay, start one with 0, and then as you go through the input voltage, the output voltage actually is dropping. So this is a trajectory with 10 picosecond between dots. So we can understand that the current that's discharging the output node, okay, is less than the highest saturation current for the V equal to 1.5 volt. Okay? So there's you get only about 60% of that on average and the effective. And then same thing for PFET, PFET pull up. So we start with the output equal to 0, right? And then input goes down. As it goes down, turn on the PFET, the current starts to flow, and then eventually output is pulled to 1.5 volt. Right? So that's the trajectory for us to understand how this the switching waveforms are constructed. Now, from delay point of view, we can construct a delay equation that looks like this. So tau is the delay we defined here. It's the average of MFET and PFET pull down and pull up delay, and it's a function of CL, of course, but it's also, let's see. So this is the delay versus load capacitance CL. As CL goes up, delay goes longer, and also it depends on the so it's basically resistance times capacitance RC, but C consists of the external capacitance and also internal capacitance. Internal capacitance further partitioned into so-called C in and C out. Okay? C in and C out is shown on the next chart. Okay? So C in is the capacitance of the next stage to be switched. Okay, we can say the gates of the receiving stage. And C out is the drain of the sending stage of the first the previous stage. Okay, and then so if you look at C in associated with the gate of the next stage. So it's mainly the intrinsic gate capacitance plus the overlap, and then you have at least two overlap, one on each side. Okay, and then C out is associated with the drain of the sending stage, switching stage. Okay, so drain capacitance, the junction capacitance, and also there's also overlap capacitance, and there's some channel capacitance as well. Okay, so capacitance, okay, the external load, that's the CL, and C out. C in is multiplied by fan out. In other words, this stage can drive more than one stage. Okay, you can drive, let's say, 2 or 3 stages, identical stage. In that case, the gate capacitance of the next stage is multiplied by the fan out factor. Fan FO means number of fan out. of course, the more stage you drive, the more input capacitance, the more C-in you have. Okay. Now, the concept of delay equation is that it, okay, this is stated here, allows us to calculate delay. Okay, notice that there are only 3 parameters for the MOSFET, for the CMOS inverter: R switch, C-in, and C-out. Okay, R switch is the slope. That was the delay, the slope of delay versus load capacitance CL. Okay. So this is like the V over I vector. Right? So R switch, MOSFET current goes into R switch, and all the rest go into capacitance. Okay. So this is very clear cut of how do you minimize the delay. You can minimize capacitance, or you can minimize R switch, which means you have to make the current larger. Current is larger, then this slope becomes less, which means that the delay is better for a certain capacitance. Okay, so 2 important factors: current and capacitance. Current goes into R switch. Capacitance go to one of these terms. Okay. Switching resistance can be partitioned into d tau n, dCl, and d tau p, and it's the average of these two. That's the CMOS inverter switching resistance, and we can write in this form: VDD over 2. Now, when the rise time and fall time is 0, okay, we discussed before, that's the saturation current. Remember that. Okay, so that, okay, CV02I, that current is the on current, but now we call it the effective current or average current in the denominator, VDD02I, and this is somewhat less than the on current, roughly 60%. So if you look at the switching trajectory again, so the effective current, of course, we only consider the effective current up to VDD over 2, 1.75. The average of this is about 60% of the maximum current, roughly. Okay, so that's the price to pay for the finite rise time and fall time. Okay. Also, it has an important implication. Let me show you on the trajectory. Notice that there's some delay spent when the gate, let's say the pull down for MFET, when the gate voltage is low. So in this case, okay, the current here is mainly determined by the mobility. Okay, not the saturation velocity, which is more important for the saturation current. Okay, so the current here, so this means that the mobility is still very important for the time where the device spent in the low input voltage steps. Okay, so next we can consider the dependence of delay. First to the width ratio. Okay, shown here. This is WP over WN. So in this case, tau n goes up with this ratio, but tau p goes down because when this ratio increase, the PFAT current increase, but MFAT doesn't change. Okay, so the average is tau n plus tau p over 2. Okay, and that's indicated by this square curve. And we indicate that for the equal rise time and fall time, we pick this symmetric value. Let's say the current ratio, saturation current ratio is 2, then we pick the PFAT width to be twice of that MFAT. But the minimum delay actually occurs before that. In other words, with WP over WN less than 2, about 1.5, let's say. Okay. But it's slightly better. Okay. There's an exercise at the end of chapter 8 that addresses this point. Okay. Next, we talk about the buffer stage for heavy loads. Okay, so if the load capacity is very large, well, first of all, let's consider the width, the width dependence of the delay. Okay. For a fixed ratio, okay, fixed N and P ratio, and if we increase the width, both N and P by a factor of K, then capacitance of course goes up, but resistance goes down. So there's no change in the intrinsic delay if you go back to this curve. Intrinsic delay is the delay when the load capacity goes to 0. Okay, so if CL is 0, you still have delay. Delay is given by the switching resistance times the device capacitance, C and CL here. And that's this value. So if I, let's say, double the width, if I double the width, the current is doubled, so our switch goes down by 2, but C and CL goes up by 2. And so that means the intrinsic delay doesn't change. But the slope changes because our switch, if you have double the width, then our switch becomes lower, which means that the delay is doesn't increase as much versus the load capacitance. Okay. So when you have a very large load capacitance, the slope is more important than the intercept intrinsic delay. And so in that case, okay, so we call that, in that case, we add a so-called buffer stage between the initial inverter and the final large load, like in this case. So consider a small CMOS inverter drive a large capacitive load. Okay. In this case, CL is very large, but our switch is large because the CMOS inverter is small. The width is small. Then the current is small, which means our switch is large. Okay. So in this case, we can improve the delay by inserting a intermediate stage between the small inverter and the large load. So now the delay becomes a two-stage delay. The first stage is the small inverter driving the buffer. This buffer, I assume that is K times wider than the original inverter. The original inverter is small, so now it's K times larger. And so the first delay is the small inverter driving the buffer. The second part is the buffer, the larger inverter driving the load. Larger inverter, R switch is smaller. Okay, R switch over K because the width is K times wider. Okay, so the total delay can be expressed in this way. And so we can see that there's optimum value of K because the sum of the second and third term is a minimum. Okay, so it's like A plus B has a minimum of a 2 square root of AB. 2 square root of AB is K cancels out C in CL. Okay, so this has a minimum of 2 square root of C in CL, which means that you can actually improve if CL is huge. Okay, so without the buffer, the delay is goes as linear dependence of CL. With the buffer, this becomes square root of CL. So obviously, if the load is becomes very large, this will be better, shorter delay than the delay without the buffer. Okay. So there are a few problems in chapter 8 that show that actually for very heavy load, you not only want buffer, but you want a multiple stage buffer. In other words, it goes like let's say a factor of 3. So you start with a small inverter. The next inverter is 3 times, and after that is 9 times, and then 27 times wider and all that. So this is again, this kind of circuit is very widely used when the signal from a small circuit try to drive either a long wire or go off chip to drive some large capacitance, and we use so-called driver, multiple stage. Okay, and it goes up, and of course, when it goes up, make sure that we use the folder layout. You use this folder layout to increase the width instead of making the width one finger with very large width. We use multiple finger and the same with the same width, and that will effectively increase the current without degrading the gate resistance delay due to gate resistance. Okay, so that's the buffer. And next, we consider the delay sensitivity. Here we can focus on intrinsic delay as a function of channel length. Okay. Now, for intrinsic delay, let's go back to that. Okay, the intrinsic delay is R switch and the capacitance. Okay. When L becomes shorter, capacitance becomes smaller, and current becomes larger. But the current goes up because of velocity saturation, so the current doesn't go up as 1 over L. Also, the capacitance doesn't go up as L because there are parasitic capacitance that does not depend on the channel length. So the current factor, the R switch and the capacitance, they do not go linear with L, but the product is roughly linear with L. You can see that this part and L is about the same slope. Okay. So that's why the bottom conclusion here is the channel length is the key indicator for CMOS performance. Okay. So if you say you have a CMOS generation of a certain channel length or gate length, then I can pretty much have a good guess of what the switching delay is. Okay, but of course, as far as bulk CMOS is concerned, the channel lengths kind of stored at about 20 nanometer. Okay, cannot be go any shorter. Even if you go double gate or FinFET, the channel length is going down very slowly from 20 nanometer towards 10. Eventually we get to 10 nanometer, but in the meantime, it's not going down fast, and that also explains why the microprocessor clock frequency sort of stalled at about 5 gigahertz or so. Okay, it's very hard to make a single microprocessor that switch faster than that because of the device delay was limited by the channel lengths no longer improve as fast as before. Okay, the delay sensitivity to oxide is much less because if you thin down the oxide, delay will improve because thinner oxide gives you a larger current, but it also gives you a larger capacitance. Right? So they tend to offset each other instead of add on top of each other. Like the channel length is good for current and also good for capacitance, but oxide thinner oxide is good for current, but not good for capacitance. Okay, we come back to the delay sensitivity to VDD and VT. Okay, we had this chart in chapter 6, showing that the delay, this is the inverse of delay. So the delay goes up as VT or VDD goes up. So we say that we don't want this to exceed something like 0.3. That case was fixed VDD and vary VT. Now we fixed the VT for fixed device, but we change VDD. And then we look at the power versus delay. Let's see. No, this is delay versus power supply voltage. So this is even steeper. So for 0.1 micron CMOS, 1.50 is the standard voltage. If you increase the voltage, delay goes down. If you reduce the voltage, delay goes up. Okay. Again, just remind you that we also talk about this in chapter 6. Chapter 6 that the performance and the power trade-off versus power supply voltage and threshold voltage. Okay, so performance, you want a performance, you want a threshold to be low, and the supply voltage to be high. But lower threshold voltage will increase the standby power. Higher supply voltage will increase active power. So there's a performance and delay trade-off, and also we can show here that if you change for given device CMOS 0.1 micron CMOS, if you change the VDD and you look at the power versus delay, okay, log scale, power is vertical, delay is the x direction, and so you can see that the supply voltage changed from 3/4 volt to 2 volts. Okay, and the delay goes down, but power goes up. In fact, the slope is very steep. So you want a high performance, the power goes as frequency to the force power, okay, the slope here. And okay, on the other hand, you want to save power, you can operate a lower voltage, okay, and then you can reduce the slope to f squared instead of f to the force. Okay. So this means that to gain, it's hard to get higher performance by going to higher VDD, because then the power really goes up very steeply. And we have a chart, okay, that shows the power, different components of power. The green, that's active power, okay, the CB squared. That's this active power, CB square F, or CMOS. That goes up with, when the gate length goes down, it goes up, but it only goes down. It goes up very slowly. What goes up, the power that goes up more steeply is the subthreshold leakage. Okay, that's why the threshold voltage cannot be reduced much below 0.2 volt. Okay, otherwise, this passive, standby subthreshold leakage power goes up for the whole chip. Active power is high per circuit, but for a whole chip, most of 99% of the circuit in the chip actually is not switching, so it's not active. That's why the slope is not steep. The dashed line is due to the gate current, okay, gate tunneling. It goes up even steeper because to reduce the gate length, oxide had to be thinner. Okay. And then at some point we switch to high K, okay, to manage this gate current. The tunneling current, the standby power dissipation due to the gate tunneling current. But in any case, we can see that the highest power we can do is about a few hundred watts per centimeter square. That's all we can manage. Otherwise, the standard or the low cost packaging cannot carry this heat away from the chip. So 1,000 kilowatt per centimeter, that's the limit. That cannot be reached. We can stay below that. And so you can see that gate length is somewhere between 10 and 20 nanometer, but it's hard to get even shorter than that from the power point of view. Okay, this chart, this is a chart from Intel, and it shows that versus clock frequency, okay, and the power supply voltage down to 1 volt. The power becomes a couple hundred watts, okay, and this is about 3 gigahertz. Okay, so by the time you go to 5 gigahertz, it's a few hundred watts, and that's pretty much the limit. We cannot cool the chip if it's close to 1,000 watt per chip. So that's okay. So next we say something about the so-called Miller effect. The Miller effect is explained here. So let's say we have a switching transistor on the left that goes from low to high, and then so the current try to charge up 3 capacitors, C1, C2, C3. The difference between C1, C2, C3 is the voltage on the other side. Okay. For C1, the V1 is held at the VDD. C3, the other side is ground. C2, however, V2 is not fixed. Instead, it's going down. Okay, the input is going up, but output is going down. And so the total charging current, okay, is the sum of the three currents. They're kind of in parallel. And so each one is the voltage on the left minus voltage on the right, dV minus V1 dt, and so on. But V1 and V3 are constant. So the first and the third term is just C1 dV dt and C3 dV dt. But V2 is different, because V2 actually is going down with, let's say, about the same slope. Okay, so in this case, we have a dV dt, but dV2 dt is negative. Okay, so let's say going down the slope with the same slope as going up. In that case, the C2 is multiplied by factor of 2. Okay, due to the fact that the other side is going down, and you try to pull it up. So in this case, you need twice the current, 2C2. Okay, and this effect is so-called a Miller effect. And this happens, for example, this happens, for example, let's say I have, yeah. So let's say this is bottom MVAT here, okay, and the gate is try to pull up. Let's see. Okay, so let's say the input is going from low to high, which turns on the MFET. The output is the VDD, but it's going down. Okay, so in this case, you have a Miller capacitance. So this C overlap actually effectively was slowed down delay by more than one C overlap. It's more like two C overlap. That's called Miller effect. Yeah. Because when you try to switch up, the drain is going down instead of being constant. You can also see the so-called feed-forward effect. You can see that when V1 is going up, okay, V2 eventually goes down, but V2 goes up first. And that's because of a capacitive coupling. Let's see. Okay. So when the gate goes up, the first effect to the drain without discharging is that the drain will go up, will follow the gate because of a capacitive coupling. Because if you give no time, then the charge of this capacitance between gate and drain cannot change. To change the charge or change the voltage, it takes time. You have to either charge or discharge. It takes time. With no time, then the first drain will go up with gate, and then the discharging current flows to discharge the drain load. Okay, so you can see clearly in the waveform that this V2 actually goes up higher than VDD before it goes down. Okay, same thing for V3. V3, let's see. V3 goes up, but if it goes down first, due to the capacitive coupling of V2. V2 is going down, so first it go down, and then you turn on the PFET, and then the V3 becomes charged up. Okay. So it's similar. It's a similar effect according to the so-called Miller effect. Okay. So to summarize the capacitance, the capacitive load of C in and C out in this particular example. Okay, so the C in and C out. C in consists of the intrinsic gate capacitance, the CG, and C overlap. Actually, it's almost 50-50. Okay, so half of the input capacitance come from the intrinsic gate capacitance, but the other 50% come from the overlap capacitance. Okay, some of it due to Miller effect. The output capacitance is the capacitance of the drain, switching drain node, and for that, the most of it is the junction capacitance. Okay, more than 50% junction capacitance. The rest are from this overlap, and also a little bit of intrinsic gate on the drain side. Okay. But you can see that the capacitance, actually the most of the capacitance actually come from overlap. Consider input output capacitance can combine. Okay, remember that the intrinsic capacitance, intrinsic delay, okay, intrinsic delay here, C in plus C out. So if you add them up, C in and C out, actually overlap capacitance is the largest component. That's why the self-aligned gate technology is so important. Okay. Before that, we don't have self-aligned, and C overlap can be very bad in the worst case situation. Then that will slow down the CMOS. Okay, and so only after self-aligned gate process, we minimize C overlap, and then we can improve the delay once we have the C overlap under control. Okay, one more chart. Here shows the effect of transport parameters. Okay, transport means that the MOSFET current. Okay, so the current can depend on mobility, saturation velocity, and the parasitic resistance. Okay, there are three factors. So when you change those, the effect will change the current. In other words, you change the R switch, that's shown here. Actually, you can see that for this sim, the most important factor is the mobility. The mobility actually has the steepest slope of the switching resistance or 1 over current versus the value, the normalized value of these. Okay, and this, as I explained, is because of in the propagation delay situation. Okay, quite a bit of the delay comes from the when the gate voltage, but in this case is MFET, is low, not all the way to VDD. When it's low, the current here actually is more dependent on mobility, not the saturation velocity. So this explains why the mobility actually is more important. Mobility is more important factor. The delay is more sensitive to mobility than saturation velocity, as far as propagation delay is concerned. Okay, so I think we'll end today's class here. So in 5 minutes, we will start the meeting. So we'll continue the rest of chapter 8 next Monday.
OK，好，谢谢，关掉，关掉。好，所以还有5分钟了哈，是不是那个